I think I've got the red boxes. Those should be the ones that I told you to do, right?
Yeah.
That looks familiar. Okay, good. I just have to keep coming over here and scroll. Okay. We answered your question. We answered your question. Anybody else got questions before we get into this?
A million, but I don't think we got enough time to go over them all.
Well, let's do the most important ones. Maybe somebody else has the same question, and it would be worth tackling.
The compound elements and mixtures.
Okay.
Use those so bad.
Compounds, elements, and mixtures. Okay. Let's start with this very simplest one, elements. Here. An element is a substance that is distinct from any other and cannot be reduced to a simpler form. It is the simplest form of the substance, which means it's also a pure substance. The only way you can reduce it any further is to bust up the nucleus. Okay, that's an element. The simplest form of the element is the atom. And the atom of one element is different than the atom from another element. John Dalton taught us that one. Okay. Now, sometimes elements occur in different forms. They can be single atoms, like helium, right? Or they could be diatomics, like those gases I had you memorize, like nitrogen. At room temperature and 1 atmosphere pressure, nitrogen is always that form. Okay, it's still an element because there's no other atom in there except nitrogen atoms. Okay. Carbon can occur like that. It can be graphite. It can be diamond. It can be buckyballs. But they're still all carbon. It's still an element.
So if you have diamond, that would be, if we had a question about diamond, it would be an element.
Yes.
We'd say that it's an element.
Yep. They just take different forms. Like diamond is a tetrahedral structure. You got one carbon here, and there's one here, there's one there, and there's one here, there's one over there, bound to that carbon. And then each one of these is also bound in a tetrahedron with others. And it's the same way all the way across the crystal. They're called allotropes. Right? They're elements, but they're different forms of that element. Okay, those are elements. If you put 2 or more different elements together, bound together in some formula, you have a compound. So you need 2 or more elements. They can either be ionic, like sodium chloride, right? Where you have the ions bound together, or they can be covalently bound compounds like water. Okay. Now, how do you get these metal, non-metal, ionic compounds? How do you get these non-metal, non-metal? They're always covalently bound. Okay. So the compound requires that you have 2 or more elements together in the formula. Whereas this one, you only have 1 element in the formula. Even if there's 2 or 4 or 60 of them, like this one, Okay, they're always just one element. If you have more than one element in your formula, you have a compound. Okay, now we're going to move to mixtures. These are all chemically bound in some form. Ionic bound or covalent bounding. With mixtures, you can have elements, compounds, with ionic compounds, covalent compounds mixed together, but they retain their individual identity. For instance, a mixture of sodium chloride in water. Okay. The characteristic of a mixture is you can separate these by physical means. You don't need chemistry to separate the sodium chloride from the water. The simplest way is just heat it, evaporate the water, and you got sodium chloride left. It never changed while it was in the mixture. Okay. That's one example. Now, mixtures can occur as either homogeneous or heterogeneous. Homogeneous means in this mixture, this physical arrangement of molecules, ions, free atoms, whatever the case may be, they can all participate in mixtures. I forgot where I was going with that. Let me back up, see. Oh, homogeneous and heterogeneous. Homogeneous mixtures require that wherever you sample your mixture, anywhere you sample it, you have the same percentage composition of each of the components. They're always, it's uniform throughout. Heterogeneous is just the opposite. It's non-uniform. It's like you stir up sand. Silicon dioxide is sand. You stir that up in water, right? And as soon as you stop stirring, the sand starts to drop out, which means depending on where you sample it, it's going to be a different composition. Sample it, yeah, go.
That's what it means by the two phases, right? That's what it means by the two phases.
Oh, by phases, yeah. Mm-hmm. Mm-hmm. Yeah, mixtures, homogeneous mixtures, heterogeneous mixtures. They can be represented in any number of different phases. Right, this is a solid, and that's a liquid. But you can mix gases with liquids, right? I drank enough of that to jump a horse every day. Pop. Carbon dioxide mixed with sugar water. It's basically what it is. So we have a special name for the homogeneous mixtures. It's called solutions. Solution and homogeneous mixture are synonymous. When you mix different phases together, you can, depending on the nature of the phases, whether they're compatible with one another, you can get homogeneous or heterogeneous. But the interesting characteristic of mixing a gas with a gas is gases always make homogeneous mixtures. There are no exceptions. You mix two gases together, they always form a solution. And we're breathing a solution right now. Nitrogen and oxygen primarily mixed together. I need to elaborate on any of this. Questions? Okay, that's good. That's the way I'd like for these review sessions to go. You know, stomping out brush fires. Rather than just having me stand up here and yammer on for an hour and a half or 2 hours. But if we need to go through these and maybe something will click in your mind and you stop me, say, I need to have that explained further. That's part of the reason we do these reviews. To give you a chance to stump the band. Okay, any others before we start looking at these one by one? Actually, we probably don't have time to look at them one by one, but we do want to hit the highlights. Okay. So we're going to take a look at, this is chapter 1, problems, homework problems from the textbook. Maybe we can knock some of these out pretty quick. Classify each of the following observations about the behavior of a substance as a physical property or a chemical property. Okay. So remember, properties are like potential. What does this substance have the potential of doing? If it's a physical property, it only describes potential physical change. In other words, like a phase change, going from gas to liquid or liquid to a solid, or going from pure substances to a mixture. But you can't go from pure substance or mixture to a compound. That would be a chemical change. So the description of that property that allows that change to happen would be a chemical property. Okay, so let's look at it in those terms. The substance does not react with oxygen at 50 degrees. That key word there is this one. That one, plus the not. It does not react with oxygen. That is a chemical property. Another word for does not react is inert. Okay, and we've got a whole list of inerts right over there. There are others, but these are famous for being inert. Gases, that group. So this is a physical, chemical property, reacts explosively with oxygen. That's a chemical property too. Does not melt when heated to 100 degrees. Right, that describes the potential physical change. Yep. Melts at temperatures that exceed 250. Another physical, yep. Okay, let's see if I can page and get to the next one. I got lucky. Classify each of the following changes as physical. Well, we've done that before. We don't need to stop here, do we? Okay. Was that? Oh no, this is not a property, this is a change, right? Maybe we better stop here. A newspaper is shredded. Yeah, it's still newspaper, isn't it? It's just in smaller pieces, right? So we've only undergone a physical change of some kind by just tearing the paper apart. It's still newspaper. Molten candle wax solidifies in a mold. It's going from liquid to solid, right? So it's a physical change. A container of unrefrigerated milk sours. Oh yeah, that's a biochemical reaction with the intervention of microorganisms. Fingernails are trimmed. That's physical, yeah. You still got pieces of fingernail scattered all over the floor if you're me. If you're my wife, they end up in the trash can, but if you're me, they're all over the place. In fact, I like to clip them and watch them fly. Never know where they're going. Maybe a cat will chase one. Let's see here. 29. We get enough of that one. Is it just A through D?
This one is one I struggle with.
Yeah, it just goes through D. Good. We need to take a look at it. Closer look. I should be writing these up here so they'll correspond to that in case that's a little fuzzy. So 129. Okay, from the information given, classify each of the pure substances. Oh, it chops it off at the end. Hold on a second. Let me see if I can move it. Hold on. I need to resize it. Hold on. Like this. And scroll over. There we go. Now we can see everything. Okay. Oh, before I forget, I need to mark Ashley present. Zoomed. There we go. All right, from the information given, classify each of the pure substances A through D as elements or compounds. I didn't make that point earlier, but compounds can be pure substances too, because they retain their identity and nothing else, as long as it's not in a mixture, the compound is pure. In fact, when you combine elements together to make a compound, it changes the identity of the substance. So, and it retains its identity in that, for lack of a better word, pure form until you do something chemical to it. So the only way that you can not have a pure substance with a compound is to mix it with something else. A pure substance cannot be separated further by physical means. I think that's a better definition. Now, chemical means, yeah, you can bust up your compound into elements and other compounds by chemical means, but it's a pure substance as far as physical changes are required. Like, well, water, right? Everybody knows how to distill water, make pure water. I mean, it's still water. It's got the characteristics of water. It's not, it could be a gas, but if it's a gas, it's still water. It's a pure substance. Okay, now back to the question. Or indicate that no such classification is possible. So we classify each of the substances as elements or compounds. Analysis with an elaborate instrument indicates that substance A contains 2 elements. We classify that substance A contains 2 elements. Analysis. This could be a mixture of the 2 elements, couldn't it? Or it could be a compound of the 2 elements that they don't say. No such classification is possible because of insufficient information. That's probably correct. We're not told enough to say whether they're individual elements in a mixture, in which case they won't be pure, or is it a compound of those elements, in which case it would be pure. So there's not enough information for A.
So you wouldn't put that one as a compound?
Right. We can't say for sure that that's a compound. Analysis with an elaborate instrument indicates that substance A, oh, yes. See, I got to read the question. Substance A, we're talking about a substance that's identified as A. It's composed of 2 elements. Yep, that's a compound. Yeah, you're right. Substance B decomposes upon heating. Well, that would have to be a compound also. If it decomposes, that's the key word here. Decomposing is a chemical change, not just melting or not just evaporation. It decomposes, it changes chemically. Okay, we have to understand what the words mean. So this would be a compound also. Heat the substance to 1,000 degrees causes no change in it. Well, let's see. What if that were an element? That would be true. Heat it to 1,000 degrees, there's no further change because in order to change it, we'd have to bust up the nucleus if it were pure, if it were an element. So it's probably a pure substance with no change, but we're not told whether we're not told enough to say whether it's an element or a compound. Because some compounds can be heated to 1,000 degrees Celsius and there's no chemical change. Heat the substance D to 500 degrees causes it to change from a solid to a liquid.
You know, this is a bad question. You agree?
Yeah, I don't like this question.
Yeah, this is not a good question. So I wouldn't expect to see one of these on an exam, not one of my exams. We have to make a lot of assumptions here in order to answer these questions. Otherwise, we've got to say that there's insufficient information. Because when they say substance A or substance B or substance C, in many cases, you have to assume that those are pure, just right off the bat. Otherwise, you can't go any further. Right? So let's set this one aside. I don't think answering this one is going to help us at all understand chemistry. Okay, let's scroll, get that one up on the board. Come on. There we go. If I have any trouble with this one, indicate whether each of the following statements is true or false. True, false statements usually cause a lot of trouble because you can think of scenarios where, yeah, maybe it's sort of gray area type thinking. That's why I never use true, false.
Thank you, Lord.
Let's see if we can answer this one and defeat the purpose of the author for creating this question. Both elements and compounds are pure substances. If they're considered separately, yes, they're pure substances. A compound results from the physical combination of two or more elements. No. It's chemical combination, not physical. If it's physical combination, you have a mixture. So that one's false. In order for matter to be heterogeneous, at least two compounds must be present. Okay, the key here is heterogeneous means it's a mixture. And mixtures can be composed of elements or compounds or some of both. So that one has to be false. It's not just two compounds. Could be elements also. Compounds, but not elements, can have a variable composition. Okay, now we have to define what we mean by composition, because you can speak of mixtures as having a composition. Right? The two components are certain percentage composition, but you can also speak compounds in terms of composition. How much of one element is combined with the mass of another element to make that compound. Right? So, okay, then now I need to read the question again, don't I? Now you're trying to figure it out, say, where the hell is he going with this? I'm thinking out loud. Compounds, but not elements, can have a variable composition. That's true. When you speak of it in those terms, elements do not have a variable composition because there's only one atom in there. So that's true. Compounds, as opposed to elements, compounds can have a variable composition. That's true. Now, if you have, once you've established a compound, say this one, that's fixed composition. But if you take those two elements and combine them differently, that's a different composition. So that's variable composition, yeah, for those two elements. Okay, let's see. How long do we have before? We need to finish on time for the lecture because the last is going to need your attention. 11 o'clock, okay. I need to get moving because we got two other chapters to get through. There's another true false. We're going to skip that. Okay. Classify the substances represented by the following models. Okay, this is a good definitional question. As homoatomic or heteroatomic. That simply means that Is the substance composed of a single type of atom, single element, or is it two or more different elements? So this one would be homoatomic, and the rest of them are heteroatomic. That's definition, that's all it is. Okay. Oh, okay. We're going to use that same diagram for 159. No. 58. Oh, he wants to take these and say, which ones of these are diatomic, triatomic, tetraatomic? Okay. Now what we're saying is how many atoms are there? It doesn't matter what they are. Diatomic, diatomic, triatomic, triatomic. So you can have a homoatomic, diatomic compound. I don't know what that gets us. You know, I think somebody just invented that so they could put their name on it. I don't think that helps you understand chemistry very much, unless you're talking to somebody about a reaction. And it's important to know how many atoms are in the compound, maybe. Okay. We've covered that already. Let's scroll to, I might just have to stay over here. Keep this thing tamed. You know what? Skip the whole bunch, because these are side by side, aren't they? See, that's a mistake I made. Let's go back. Okay, we're good there. How about your chemical symbols? You feel comfortable with those? You've done the flashcards till you're bleary-eyed? Okay, that's good. Write the chemical symbol for each member of the following pairs of elements. I put the ones in here that are very often confused. It's easy to get them mixed up. Like sodium, see 153. Sodium, like sulfur. Magnesium, Mg. Manganese, Mn. Calcium, cadmium. The calcium came first, so it gets the Ca. Cadmium came later, so it's the poor stepchild. It has to be Cd. Arsenic. Oop, that's argon. Argon took the R first, so arsenic is stuck with S. And there's argon. All right. Okay, we did the left side already, so I'm scrolling down through the right side of this page. Anybody have trouble with this one, or do you care? Following diagram has different colored spheres representing atoms of different elements. There we go. Select a diagram or diagrams that represent each of the listed situations. There may be more than one correct answer. Which diagram represents a compound whose molecules are triatomic? Oh, okay, here we go. Molecules are triatomic. Well, one, except, what was the question again? A compound. So that number one, Roman numeral 1, is triatomic. And that's a compound. Number 2 doesn't have any triatomics in it. Number 3 has triatomics of different kinds, but it's not a compound, it's a mixture. And 4 is a triatomic compound. So I would interpret that as saying Roman numeral 1 and 4 answer that. I think we need to move on.
I have wrote down for questions for you for 83 or 81, 83, 85, and 87.
Oh, do you want to do those? Is that what you're saying?
Yeah, I did. Those are the ones I struggled with.
Okay. Yeah, we'll spend time on those. 81 is the first one.
Yeah, 81, number B, or
81.
letter B.
Let me move over on this side. There it is. 81. Write a chemical formula for each of the following substances based on the information given. All right. A molecule of hydrogen cyanide. Molecule, it's got hydrogen in it, right? Cyanide. That's not an element. There's no element up there, cyanide. It's a polyatomic, right, from that list I gave you. So cyanide is Cn with a -1 charge. That's the cyanide polyatomic ion. Combined with hydrogen, which is a +1. In nearly all combinations of hydrogen with anything else, it's a +1. There are instances where hydrogen becomes a -1, but those are easy to spot. If hydrogen is the second element and the first one is a metal, then hydrogen is going to be -1. In this case, sodium would be +1. That's sodium hydride. Whereas this one is hydrogen cyanide. Just to show you the difference. Okay, so let's finish to A. Hydrogen cyanide, yeah, is triatomic. That's true. 1, 2, 3. Contains the elements hydrogen, carbon, and nitrogen. Hydrogen, carbon. Yeah, that's true. Write the chemical formula. We did that. Yeah. Okay, that's A. B, a molecule of sulfuric acid has heptaatomic and is heptaatomic, which means what? 7 atoms. Okay, has 7 atoms. And contains 2 atoms of hydrogen. Okay, 1 atom of sulfur. And oxygen. Okay, it told you got 2 of these, 1 of those, and 7 total. So that means 1, 2, 3, and 4 more. Okay.
So it just wanted you to figure out.
Yeah,
the
just
atoms of oxygen.
use the statement. Yeah, use the statement to fill it in.
Look, had me all confused trying to go back down and read it.
I was like, I don't even know what it says
They
to
were
me
broken
right now.
down different
But
ways.
that's not the first time I've heard that. That I think they, I don't know who picked that book. But I would have picked it different. That's actually, it's got too much in it. You don't need all those chapters. Not for this course. You can probably do the book like that.
I wish
And
I
that gives you
was
plenty.
on that video.
But changing a textbook around here is, oh, it needs an act of God. And I ain't him. Okay, 81 and then 83.
83B is the one I have trouble with.
83B, okay. In each of the following pairs of chemical formulas, indicate whether the first chemical formula listed denotes more total atoms, the same number of atoms, or fewer than the second. Okay. You say B?
Yeah.
Okay, so we got 183B. And we're looking at calcium sulfate versus magnesium hydroxide. Okay, total atoms. This one should be easy. Just add up your subscripts.
1 plus 1 is 2 plus is 6. 6 atoms.
Now that you did the last question, this one kind of seems simple now.
Oh, the last one, yeah. And then in this one, whenever you got parentheses, you got to be sure and propagate that subscript through the entire group. So that means you have 2 oxygens and 2 hydrogens. So 2, 4, 5. So that one, the calcium sulfate, the first one has more.
That's fair.
So you can probably do the rest of
Yeah.
it. Okay. By the way, when you see parentheses like this with a subscript, it's a little more difficult when you have only one. Like this one, that's a polyatomic sulfate. Right? It's a group of atoms that behaves like a single ion. And the charge on that is 2 minus. But that charge is spread over the entire group. It cannot be localized to any one atom. That's what they behave like a single unit. But when you see a parentheses like this, oh, that's a dead giveaway. That's got to be a polyatomic. And that's got to be a polyatomic. And that's definitely a polyatomic. That's acetate, right? Change the magnesium to a hydrogen. 1 hydrogen, what do you have? Well, if you have a 5% mixture in water, you have vinegar, acetic acid. Okay, another one.
87, and that one I just left blank because I have no idea.
87. Let's see, why don't want to go? Oh, maybe it's over with and I just need to scroll over and get the other side. Yeah, that's what it is. Here we go, 87. All right. A mixture contains the following 5 pure substances. I guess we better write them up here. into H4, NH3, CH4, and CH3, Cl. Okay, do we need this information here to get to the one? Did you say the last one gave you trouble?
They don't,
Oh, they all did.
yeah, I left it blank because I.
Oh, okay. How many different kinds of molecules that contain 4 or fewer atoms are present? 4 or fewer atoms. So that one's fewer. That one's 6. That one's 4. That one's 5. This was 3, 4, 5. Okay, so they only have these 2 or 4 or less atoms. A mixture contains the following 5%. How many different kinds of molecules that contain 4 or fewer atoms are present in the mixture? Okay, that's the way I interpret that. Okay. That one and that one do. How many different kinds of atoms are present in the mixture? Different kinds of atoms. How many different elements are there? Right. There's nitrogen. There's hydrogen. Nitrogen, hydrogen, carbon, chlorine. So there are 4 elements in that mixture.
On that question, you don't do anything with the numbers.
Mhm. How many different kinds of atoms?
Okay.
There are 4 different kinds, which means there are 4 elements. They should have said that. How many elements are in that mixture?
I remember that one now. I didn't know if I need to add the numbers and all.
How many total atoms are present in a mixture sample containing 5 molecules of each component? So if you've got 5 of each of these, right, times 5, isn't that what that says? 5 of each, okay? You got 2 here, so that's 10 total, right? You got 6 here, so that's 30. And you got 4 here, so that's 20. You got 5 here, so that's 25. You got 1, 4, 5. 5 times 5 is 25. Let's see if I can do this in my head. Let's see, that's 50, 60, 70, 110. Got 110 atoms in that mixture. Did I go too fast?
No.
Okay,
I just wish that they would have separated B and C, but not having like the same. So that one says how many different kinds of atoms, and that says how many total atoms. I got really confused on
Yeah,
those.
yeah, their wording is messy, huh?
I just thought I multiplied the top number, the B by 5.
Oh, no. No, they're separate problems. Yeah. Okay, one more. How many total hydrogen atoms are present in a mixture sample containing 4 molecules of each? Now instead of 5, it's 4. Okay, 4 molecules of each. Total hydrogens. No hydrogens here. 16 hydrogens there. 12 there. 16 here. And 12 here, right? Okay, let's see. That's 8 and 8, 16. Carry the 1. 56. Okay. I don't know, over the years, the hardest thing for me to do is not overthink a problem. Trying to read into the problem what's not there. So that's why I'm pretty adamant about finding out what's the question. And you see, I still do it. I read the problem and I don't really understand what the question is. So when I get to a point and I say, wait a minute, this doesn't make any sense, I go back and say, oh, I had the wrong question. I was trying to answer the wrong question. Okay, 87, any others in this group? We go to chapter 2. Okay. Let's see. Close that and go to chapter 2. Open with, we might make it, if we're lucky. And I gotta boost this one up again.
Is this exam gonna be online or paper?
What's gonna be what?
The exam, is it online or paper?
Oh, right here. Yeah.
Is it set up like how the homework problems are, like 1 A, B, C, D? Or is it just like question 1, question 2?
There, I tend to lean toward multiple choice simply because I can grade them faster. What I want to do is get them graded before you walk out of the room. So you know if there's any problem. I've already got it made up. Let me just look at it and see. There are some bonuses.
Oh, thank God.
Wait a minute.
Oh,
Wait a minute. That's exam 2. Excuse me. Let me see.
probably not gonna get bonuses. So
Yeah.
Yes, and if
you got it right, you got it right.
yeah, I guess if y'all.
Oh, well.
Yeah, there are some bonuses on this exam. And multiple choice. Okay, looks like they're all multiple choice. Yeah, they're all multiple choice. Now you got to be careful with multiple choice. Because in order to make a multiple choice do what it's supposed to do, in other words, find out what you know, sometimes it's got to be a little tricky. So you got to stop and think. First, don't do like I do. Like find out what the question is first, and then look for the answer. And if you're sure you know the subject that's being addressed in that question, and you look at the choices, and none of them seem to match what you think, pick the best one. Especially for those that require calculations. Your rounding might be a little bit different, but if you've done the problem right, then you should get an answer that's very close to the one that's available in the multiple choice. And then that's the good thing about taking a paper exam. I'm going to be here. If you have a question, ask me. And I'll tell you whatever I can without giving you the answer.
Come on, just give it to me.
Be a sport, huh?
Yeah.
Let's see, we need to go bigger, don't we? There we go.
can always tell me you did so good in the class, you need a pay raise.
Yeah, like that's gonna be. I think they work on a formula that's set out by the state government. And at least that's true for adjuncts. They pay by the credit hours for the course and how many students are in the class. For this class, I get the full load. But with my other class, there's not enough students to get the full value for each credit hour.
That's not fair.
But I figure I'm already coming here for this class. So it's kind of like, in Louisiana, they call it lagniappe. You ever heard that expression?
No.
It's a Cajun word that means something a little bit extra. By the way, I lived in Louisiana for 13 years and I never saw something free for a little bit extra. That's just the word that they use. I went to a festival called Lagniappe on the Bayou. And everything you got down there, you had to pay for. That's a misnomer. There's no lagniappe on this location. Okay, chapter 2. Let's see, here we go. I'll be able to knock some of these out pretty quick. What's the main reason scientists prefer to use the metric system of measurement rather than the English system? One word, decimal. Decimal system allows you to make unit changes much, much easier. Just move the decimal. It's simply because our numbering system is 10 digits for precision. Whereas with the English system, I mean, the unit conversions are all over the place. Like 1 inch used to be like 3 barley kernels laid end to end. That was an inch. And a foot was the length of the king's foot. So that changed every time we got a new king. One that we don't use anymore is I painted myself into a corner. The cubit. Right? If you read the King James Version of the Bible, it talks about cubits a lot. Cubit was about 18 inches, just from your elbow to the tip of your middle finger. Right? So that varied depending on the person. Anyway, I digress and I'm wasting your time. So let's move on to 2.3. Complete the following table by filling in the blanks in each row with the name of the metric system prefix of the abbreviation and or the power of 10 to which it is equivalent. The first row has been completed as an example. First row has been, oh yeah, it has. Okay. So millime is abbreviated by a little m, and it means 10 to the minus third times whatever the base unit is behind it. How about this one? What does that mean? That's short for giga. Right? Everybody knows gigabytes, right? That's a billion. So it's 10 to the 9. It's a giga times whatever it is. A gigabyte would be a billion bytes of storage capacity in your computer. A nano, abbreviated with a little n, means what? Just change the sign. 10 to the minus 9. A nano is a billionth of. Okay, so we're going to start from this end. 10 to the 6th. Right? If this is a giga, 10 to the 9th, 10 to the 6th is a mega. And it has a big N prefix. And this little squiggly thing looks like a U is actually a Greek letter mu, mu. And it means micro. And it stands for 10 to the minus 6th, or a millionth of. Okay. Oh, before I get going too far, are there any in chapter 2 that we need to focus on? That gave you trouble? Or did you just breeze through chapter 2? Did you get that far? Oh. Let's see, we need to scroll to the side, I think, to stay in order. No. That was filled in already.
Can you go over 17?
Mhm.
Because I didn't even answer it, so I must have struggled.
Okay, all right, 17. Identify the estimated digit in each of the following measurements. All right, when I discussed this in class, I referenced the digits in a number as either certain or uncertain. The uncertain one is the estimated one that they're referring to here. And which one is the estimated? It's always the last one. Everything else is certain. The last digit to the right is the estimated one. So the estimated digit for this one would be 4. The estimated digit for this one would be 0. This one would be 4 as the digit, and this one would be 4.
So it's just always the last number.
That's the estimated one. You estimate because the measuring device has no mark or indicator whatsoever for the number. It's between two indicated values. Like if you have a meter stick or something, it's marked off like that, and you're measuring something that's this long, it's between this one and this one. So you estimate the last one. What did I do with that? Need to put a beeper on it so I can find it. We'll leave it there. Okay, there we have another one. Let's see.
I think 23, I couldn't figure out the back of the book, I couldn't figure out how they got 0.1 for both of them.
Okay, consider the following rulers as instruments for the measurement of length. So we're measuring the length of that paper clip, right? Okay. Where did it go? It must go down here and to the left. Yeah. What would the uncertainty be in measurement made using the following? Ruler 1 or ruler 4? All right, so let me go back up. We want the uncertainty in this one and this one?
Yeah.
Okay. Well, which one are you estimating? If it's between 2 and 3 centimeters, then I would estimate this one at maybe 2.7 centimeters.
I think that's what I put as my answer, and then it was 0.1, that's right, I confused that.
Oh,
It's like the
Okay.
answer is 0.1, but I put 2.7 as the answer.
okay, let's look at the wording again. That's probably where the problem is. What would the uncertainty be in measurement made using fine? Okay. What position, at what position is your guess made? It's made in the 0.1 position.
Okay,
Yeah, 0.1.
so I just didn't read the question.
Yeah.
Pretty much.
This one is 10, 20, between 20 and 30. So it's 21, 2, 3, 4, 5, 6, 7, 27, right? And then there are markings on here for the 1 centimeter, the centimeters. And the last one you estimate. So you estimate this one, it looks like it's right on the line. So you estimate the last one is 0.0, but the position that's estimated is the 0.1 position. I think that's what they meant. Okay. Any others? Let's see. I'm on a new page, so I'm going to go left. 29. Number of significant figures. Anybody have trouble doing those? Just use the rules, right? Yeah. If they're all non-zeros, they're all significant. And then you got three types of zeros. On the left, captive in the middle, or on the right. On the left, they're never significant. In the middle, they're always significant. To the right, it depends. Is there a decimal? Is there an explicit decimal in that number? If there is, then the zero on the right is significant. If there's no decimal there, then the one on the right is not significant. Okay. All right, so let's see. Let's scroll to the right. And go back here. There. Number of significant figures, estimated digit, magnitude of uncertainty. We didn't talk about this very much. I think what they're saying for this one, as your example, is that's just identifying the position that we talked about earlier. What position is the uncertain digit? In this case, it's the 100th position, and that's because the 100th is an estimate. So they're saying plus or minus 1, but statistically speaking, that may not be true. It's the correct position, 0.01 position. But you don't know the actual uncertainty of your measurements until you make 2 or more measurements and you actually do the statistics. You see what's the spread, and you use an analysis that tells you what's your confidence in that number. But for the sake of argument, we'll let them get away with this one and say, whenever the position is in the 100th, then it's plus or minus 0.01. If the position is in the 10th, it'll be plus or minus 0.1. If the position is the 1 position, then it'd be plus or minus 1. Okay. Just recognize that if you're, do they give you any statistics in MLT? They do.
Yeah.
Okay, are they going to do like means and standard deviations and that type of thing?
Yeah, we're going to be.
Okay,
We done main.
okay.
Not really that's-
No.
Standard deviation or standard error, maybe?
Not
No.
Not yet.
Okay. Usually when you're confronted with a governing body that certifies your lab, they're going to want to know those things. Right? They'll either want it in terms of standard deviations, plus or minus error ranges, maybe something to tell them, you know, what's the spread on your values. Okay, so we don't need to do this one. You just take the very last one. This would be plus or minus 1, plus or minus 0.01. How about this one? Right, those 2 zeros are not significant. So
So we
be
go with 2.
plus or minus 100. Because this is the last one that's significant, and it's an estimate. Okay, I'm glad we stopped here.
So for D, you go to the 5, but it would be plus or minus 10.
Right. Now, what if I did this?
Then you have the
Plus or minus what?
1.
Okay, right? Because now those zeros are significant. It's all in the decimal. Now there's an implied decimal, of course, right here, because that tells you where ones, tens, hundreds. But as far as significant figures goes, you've got to have an explicit decimal to determine the right-hand zeros, whether they're significant or not. Okay. Let's scroll a little more. Round off each of the following numbers to the number of significant figures indicated in parentheses. Okay, anybody having trouble with rounding? Right, it's the 5 rule. You look to the right of the number that you need to round. So if it says 4 here, 1, 2, 3, 4, then you look to the right. That's greater than 5, so now this is 8, and those drop. Or 3, 1, 2, 3, that was less than 5, so this one stays 4, and the 3 is gone. Okay. Go back over to the left, pick up keep them in numerical order. How about this one?
Yeah, let's go over that.
Without actually solving, indicate the number of significant figures that should be present in the answers to the following. Multiplication, division. Okay, that's important, because when they say without actually solving, the only operation that will work on is multiplication division. Because all you have to do is look at the least number of significant figures in the operation, and that determines your answer. Right? For this one would be, there's 5, there's 2, there's 3. This is the least. So this one's going to be 2 significant figures in the answer. Number of significant figures, yeah. This one would be 2, 3, 3. So you're limited to 2 here. But this one, 2, you're limited to 2 in this one. And this one's 2, you're limited to 2 in that one. If you've got addition and subtraction in there, you have to solve the problem in order to know. I don't know if any of these are examples, but I've seen them where you have, you're adding 5 significant figures, 1. Well, let me change that. Say 4 in this one and 4 in the next one, you add them together, your answer's got 5. Why? Because you line up the decimals and you look at the significant figures in there. For instance, let's make one up. Let's say you have 123.4, and then you add to that one 35.67. How about that? So that would be 7, 10 carry the 1, 8, 9, 5, 1. Okay, how many decimals can we keep? This is the least one. This is significant, so we keep it. And you chop that one off. So this is 7. That means this one is now 1. 159.1 is your answer. This has 4 significant figures in it. Well, coincidence. That one has 4 and that one has 4. Let me see if I can figure one that doesn't obey. How about let's change this to a 0 here. And a 1 there. How about that? So we said 1, this is addition. 1, 8, 5, 1. So how many do we get to keep? We go to the least to the right. That 0 is not significant. So we have to stop here. Okay. That means this one has to be rounded. That 1 drops. It's not big enough to increase this one. So it's 1, 5, 8, and we need a placeholder, but that placeholder is not significant. So if we add 3, 3, and we get 3. I was trying to make one up where we get 4 out of 3. It does happen. The point is, with addition and subtraction, there's no way to know significant figures in your answer without doing the calculation. Whereas multiplication division, simple, just take the least number and that's it. Okay. Let's see, let's scoot over to the side. All right, anybody have trouble with 251? How to line up the decimals? So no trouble. Good. Okay. Scientific notation. We're good there. Coefficient needs to be between 1 and 10. Right. And depending on which way the decimal moves determines the sign on the power of 10. If it moves, in this one, if you move to the right, 2, what's the sign on 10? Negative 2. You're storing up negative information because this is small. You're making it larger. So the power of 10 has to be smaller. When the coefficient gets bigger, so the number gets bigger, then the power of 10 has to get smaller. So we're making this one bigger by going 2 to the right. We have to make this one smaller by going 2 the other direction. Okay. Need to do the rag over here. This side. Okay. Let's see. Oh, that is the right hand side. I'll go back to the left. Scroll down. Scientific notation. You just have to, you've got to be aware of the number of significant figures in your number. Like this one only has 3. So when you move the imaginary decimal over here, 1, 2, 3, 4, it's 10 to the 4th, of course. But what's your coefficient? It's 2.31. That's it. You don't get to keep the zeros. How about this one? Go back the other way to standard notation. So let's take this one. That one is 1,000th times this one. The decimal has to move to the left, correct? Because this one's disappearing, it's getting bigger until it disappears. And that information is reinserted into this number, which means left 3. Let's see, operations. Correct numbers, significant figures. Okay, all of these are multiplication and division. That's good. So what would you do with your calculator? Right, is everybody familiar, able to do scientific notation in your calculator, put numbers in? Okay. So how many can you keep with this one? There's 3 there, and there's 4 there, so you can only keep 3 in the answer. That's 3, 3, 2. You can only keep 2 here. That's the nice thing about scientific notation too. But if you create the number correctly, or if whoever created it does it right, the significant figures are there in the coefficient. You don't have to guess at what the zeros are worth, because in the conversion, if you've got non-significant zeros, they drop out in the coefficient. Let's see. This one is 2, 2, 2, and 2. So the answer will have 2 significant figures. Now, when you do a series of calculator operations, that are only multiplication division, I let my calculator keep all the decimals that I can. And go through the whole thing. And then at the end, determine what the advantage of that is, it avoids rounding errors. If you do this one and round, and then do this one and round, and then do them together and round, there's a good chance that you're going to be way off. So you keep all your decimals until the end, as long as all the operations are multiplication division. If you've got any addition, subtraction in there, you have no choice. You've got to do an intermediate step. Okay. So where would we have, as a practical matter, where would we have an intermediate step in the lab situation? Well, the example that we've given is you're measuring out a liquid in 2 different containers. One of them is more accurate than the other. So when you add those values together, you combine the volumes, you're limited by the least accurate one. And that implies significant figures. Okay, let's see. I'm already on the right, yeah. So we'll go back to the left. How about this one? Using dimensional analysis, convert each of the following measurements to meters. I have trouble with that. Unit conversions. That as a general concept, is that giving anybody trouble? No? Good. Good news. Good. Did you do this one? Convert the mass in grams to pounds. Good with that one? You have to look up the conversion factor though, because it's not given.
And the conversion factors can be given on the exam.
Should be. Yeah, hold on a second, let me check to be sure. They'll either be in the problem itself. Well, they'll have to be. I was looking for a sheet that sometimes I tack on the end of an exam called useful information. So I don't see one for this one. So if you need a conversion factor, it should be in the problem. Now, if you need one and it's not, ask it, because it should be there. You shouldn't have to go look it up. So what is the conversion factor here? If you're going from grams to pounds, let's see, 281. 1,550 grams, and you're headed for pounds. Right. So do we know a conversion factor that will go from grams to pounds? Pounds on top, grams on the bottom, right? Because we want to cancel grams. So what's the relationship of grams and pounds? I know what it is. I'm just seeing if you do. 454 grams is 1 pound. So you just divide 454 into 1550. How many significant figures will your answer have? 3. This is a conversion factor, which means it has infinite significant figures. All conversion factors are that way. So really, when you're doing a conversion like this, all these conversions, if you have to chain more than one together, the only one you have to consider is this one. Okay, so your answer will have 3 significant figures. Looks like about 3 point something. Just estimate. 3 what?
3.4.
3.4. There you go. 3.41 pounds. Oh. Okay. Let's see here. Works in my pocket. Scroll to the right. Top of the page. Okay. When each of the following measurements of volume is converted to liters. Okay, so there you're given the conversion factor. A conversion factor is derived from an equivalence. Something equals something else. And then your conversion factor is just the quotient based upon that equality. So depending on which one you need, you could have liters on top or liters on the bottom of your conversion factor. But the conversion factor is always a quotient. And it's based upon an equivalence. So unless you want me to, I don't think we need to stop there. Density, anybody having trouble with density? You did? Okay. Oh, with one of these, which one?
I think it was 93.
Acetone, solvent in nail polish. Some nail polish removers are not acetone. You can tell by smelling them. Acetone has a very distinctive smell to the odor. And if it doesn't smell like that, it's something else, probably ethyl acetate. You remember, I don't know if you are old enough to remember the whiteout in the bottle with the brush.
Yeah.
Okay, before they came up with the tapes. Yeah, that had an odor to it. Most of those were derived from ethyl acetate as the solvent. So some nail polishes, if it says acetone on the bottle, obviously it's acetone. But if it doesn't say what it is and you smell it, you know what acetone smells like because you've used a nail polish remover. If it smells different, then it's probably ethyl acetate. And that's what was in those whiteout bottles. Oh, okay, so let me get back to the topic here. Chopped off more than it is on the screen here. There we go. Okay. Acetone has a density of 0.791 grams. 0.791 grams per milliliter. That's typical for liquids. Liquid densities are reported in mass per milliliters or liters. Liquids and liquids are per milliliter. Gases are usually per liter, and solids are usually per cubic centimeter. And you remember cubic centimeter and milliliters are equal. So all you have to do is just change the unit and keep the number. But in this case, that's acetone. What's the volume in milliliters of 220.0 grams? So mass is 20.0 grams. So what's the formula? We've got a formula that we can use to solve it, right? E equals what? M divided by V. Yeah. So remember, anytime you've got a formula like that with variables, if you've got a value for, in this case, two of the variables, you can find the third one. Okay? Any equation that's got one unknown, you can solve it. So
the grams and the grams cancel out, and left with milliliters.
well, I would solve it for the question first. What's the volume? So let's solve it for the volume. Correct? Okay, now you can plug in your values. 20.0 grams, 0.791 grams per milliliter. Right, grams cancel. Leaves you with milliliters. The denominator of the denominator is the numerator. So this flips and puts the milliliters on top because it's in the denominator down here. Yep. And it's good to check your units of measure. Right? That helps you determine whether your answers are right. If you follow the units along. That's part of the dimensional analysis part. You're analyzing the dimensions to get the answer. And a lot of chemistry is like this.
Just simple unit conversion. Once we get to balancing chemical equations, then we're going to use those chemical equations to determine if this much reactant goes in, how much product comes out. We're going to be able to do that. All right. Let's see. We got 20 minutes. We're getting close to the end here. That's density. Temperature scales. Anybody have trouble with temperatures? All right. How do you convert between Celsius and Fahrenheit? The one that I remember is Fahrenheit equals 9/5 Celsius plus 32. Or your book might say 1.8. But if you know that one, that's the only one you need to know. If you have Celsius, use this one. If you've got Fahrenheit, either plug it in and solve it, or solve it and plug it in. Either way works. How about Kelvin and Celsius? Kelvin equals Celsius plus 273, right? Okay. Where's my cursor? There it is. All right, that's it for that chapter. Chapter 3. Okay. There it is. I was waiting for that. Thank you, Adobe Reader, my default. Okay, let's bump it up to, there we go. Right, before we run out of time, are there any in this group that we need to attack first? Okay. Which subatomic particle correctly matches each of the following phrases? Possesses a negative charge. That's an electron, right? Okay. Has no charge. Well, if we're stuck, our only choices are subatomic particles, then if it's neutral, then it has to be a neutron. Has a mass slightly less than that of a neutron. That's the proton. Neutron is a little bit heavier. Has a charge equal to but opposite in sign from that of an electron. That's another proton. Equal size charge but opposite to an electron. All right. Oops. Go over here since we're moving to a new page. How about this? You have any trouble with this symbolic notation in telling you how much of each one is there? Right. What element is that? SN. Yeah, it's right over here.
I don't remember
It's
that
one of,
one.
it's one of those Latin names.
The S's I get a little confused on.
Yeah, SN is 10, yes. The Latin word for that is stannum. So if you look on your toothpaste tube, it'll have stannous fluoride in it. That's how they get the fluorine in your toothpaste to help strengthen your teeth. They put it in there as the salt of tin and fluorine. Because your body doesn't absorb tin. So it's not toxic. Let's see, that's gallium, that's magnesium. How about this one?
That one might be wrong, but is that one plutonium?
Plutonium is Pu.
Oh, yeah.
This one's next best thing to gold.
Platinum.
Yeah, there you go. Platinum. Okay, so how many protons, neutrons, and electrons are in each one of these? Well, remember the way we write things right there. This is the Z and this is the A. That's the number of protons. This is the protons plus neutrons, the mass number. So, and these are all neutral, correct? So this would have 50 protons, 50 electrons, and 68 neutrons for this one, for that isotope. And just do the same thing with each one of them. Let's see, do we have ones for ions? That would be a good one to go to. If we can do that same type of calculation, only using ion. Okay, we'll come back to that one in a second. Let me look over here. All right, let's go back to that table. There it is. Complete the following table. Let's do that. How about that? Did anybody have trouble with this one? No? Oh, but we don't need to do it.
What number is that one?
Oh, this is 319. We're all good? All right. We'll move along then.
I had trouble with that one.
Okay,
Yeah, let's go.
this determines the atomic weight of naturally occurring element when given composition information for the isotopes. So for this first one, we know that the analysis tells us that there is 7.42% of the lithium-6 isotope. And its actual mass is 6.01 atomic mass units. Now, why is it not 6? You remember? There's only one isotope in the entire periodic table that has a whole number value with infinite zeros. That's the standard. Carbon 12. Carbon 12 isotope is 12.00000000 by agreement and definition of the scientific community. Everything else is referenced to that. So all the others isotopes will have fractional values. And that's why this one is 6.01, not 6. Now this number represents protons plus neutrons, but it doesn't say what the mass is. It just says numbers of protons and neutrons. This says the mass is 6.01 for that isotope. This isotope is 7.02. So how do we calculate the weighted average of isotopes in nature? First, you need to know the abundance. That's what this is. Okay. Then you need to know what's their atomic mass for each of the isotopes. Then you say, what's the contribution of 6.01 atomic mass units? 6.01 atomic mass units. The relative abundance of that is 7.42%. But if you multiply 7.42 times that, you're going to inflate it by 100 because it's parts per 100. So you need to use the fractional equivalent. What fraction of the total is that isotope? It's 0.0742. There we go. That's the contribution of this isotope to the average atomic mass in nature. The other one is 7.02, and its abundance is 0.9258. Okay.
So you just multiply those?
And add them together. That's the weighted average. So 6.01 times 0.0742 is, I must have hit a wrong button. Let's back up and try that again. Come on. What seems to be the problem? There. Let's try it again. 0.0742, unless somebody beats me to it, is 0.44594. Notice I kept all my decimal places. Actually, I better not, because we got to add these together. This is going to be limited to 3, right? So it would be 4.6. There we go. This one is 0.9258 times 7.02 is 6.499. 3 places. 6.499 would be 50, wouldn't it? Rounded off. There we go. So that needs to be rounded off here. 6.95 atomic mass units. That's the weighted average atomic mass per atom of naturally occurring lithium. Now, if you search around for an isotope or any atom, any individual atom with that mass, you never find it. Doesn't exist. This is an average atom. It's a mathematical creation. And we use that because when you're doing chemistry and you need to use these values in your calculations, you don't have the equipment or the time or the need to separate out the isotopes for your chemical reactions. You need to know something about the naturally occurring lithium or sodium or oxygen, whatever the case may be, without having to go through the isotope. So we have people that spend their entire lives doing this stuff, and they report those values in the periodic table, right up here. In this table, it's upper left-hand corner. Those are weighted averages of naturally occurring elements, taking into account the relative abundance of all the isotopes. So that's why carbon-12 isotope is 12.0002 to infinity. But there's also carbon-13 out there. So when they report the value for carbon, it's 12.01 rounded off, simply because there's a little bit of carbon-13 that skews the average, the weighted average, up a little bit. Okay, and you can do the same thing for the rest of them. This one, it takes a little more because you've got 1, 2, 3 isotopes. You just do the same thing and just add them all together. Okay, let's see. Oh, true, false. No, we're not gonna do scroll over because we're getting into a new page. Go down, down, down here. Write the complete chemical symbol for the isotope of chromium with the following individual characteristics. Anybody have trouble with that one? Good, because we only got 10 minutes. Specify the location of each of the following elements in the periodic table by giving its period number and Roman numeral of the group. Okay. This, you'll remember that the extra credit where I had to fill out the table across the top, that you wanted the group numbers, but those were the new system, 1 through 18. The old system is Roman numeral. So you have Roman numeral 1 for this one, Roman numeral 2 for that one, and then Roman numeral 3 for this one. And these are all A's. Here, these 2, and these last 6. When you get down here, we got a different set of Roman numerals, and these are all B's. Simply because of the octet rule. This means that there's one valence electron here that this lithium can lose, make it a positive 1. This one has 2 valence electrons, which it can lose and make it a positive 2. Same for everybody in that group. Over here, you have 3. It can lose those 3 electrons and make it plus 3. Or this one can either lose 4 or gain 4 and make an octet. So it can be plus 4 or minus 4. And then if you work from the other side, this Roman numeral 7, if you add 1, you get 8. So that makes it a minus 1, is its preference. So that's why the Roman numeral system was used. And it has its advantages. But if you can count, you can say, okay, 1, 2, 3, 4, 5, 6. 6 valence electrons. If it needs 8, is it easier to lose 6 or to gain 2? Gain 2. So it gains 2 electrons, which imbalances the charge toward the negative, 2 negatives. That's why everything in the chalcogens is minus 2 when they're charged. You'll see other numbers in here. And that's a different system. Sometimes it's charged and sometimes it's oxidation state, which is another bookkeeping system that I hope we'll get to talk about. But when you're writing ionic compounds, you're using a non-metal and a metal, then the charges stick. These are minus 1, minus 2, minus 3, plus 3, plus 2, plus 1, and then these are variable. When we name compounds, that's what we get at. All right. Let's see. Metals and non-metals. You know the difference there, right? You know the dividing line right here. That's stair step. Non-metals, metals. Okay. Let's see, I skipped the left-hand side. Let's go back up. Oh, and I got talking and forgot about the period part. Periods here are numbered from top to bottom. That's always been the case. First period only has helium and hydrogen. Second period here, third period, fourth period, fifth period, sixth period. Did we write the electronic structure of an atom yet? We didn't do that. Okay. That's all right. I won't mention that. If you ever have to do that, the structure of the periodic table will help you do that. I mean, you can do it longhand, hard way, or you can use your periodic table and do it really quick. And knowing the electronic structure of an element helps you understand why it reacts the way it does. Okay. Let's see. More, get this one. Well, if you know your way around the periodic table, these should not be trouble. Wait a minute, we did do electronic configuration, didn't we?
Is it the one where it like?
Yeah, where,
A3 or?
yeah, where you have, well, let's do carbon, right? Carbon has 6 protons and 6 electrons, right? So the first 2 electrons go into that orbital.
Is
Okay,
it the diagonal thing?
Yeah.
yeah,
Okay.
that's it. So got me doubting myself now. And then 2p2. Right. So that's the electronic structure for carbon. Has 2 electrons in this orbital, 2 electrons in that one, and 2 electrons in that one. And you can tell if you just work your way down, right? Where is carbon? It's in this group over here. All of those elements on this side in this are filling p orbitals, right? So in the second period, those s orbitals are already filled. These are already filled. 1s2, 2s2. Now you're into 2p, 2p1, 2p2. There you go, carbon. And that way, I mean, you can do it quick that way.
After I said no, I thought about it. I was like, wait, the diagonal thing?
Now, when you get down to, say, period 4, and let's go out to maybe, I don't know, nickel. Nickel has 28. Right? So you've already gone through the 1, the 2s, the 3s, now you're starting on the 4s. And we can use shorthand here too. Noble gases are complete. That's why they don't react with anybody. They have complete orbitals. So if you go back to argon, argon 18, as your base, that's your starting point. Then you can go from here and then go down to here and say 4s2. Right? And then, but when you get into here, which orbitals are being filled in this group right here? The d orbitals. Gas P, D. But now with the D's in this period, we got to back up 1 to 3 D's. That's why the diagonal works. It makes you do that. So 4s2, and then you go back to 3 D's. And the D's fill from left to right. 1, 2, 3, 4, 5, 6, 7, 8. D8. Right? And that should be 10 plus 18 is 28. So you got all your electrons there. But to do argon, you just fill up these orbitals. Right? Fill up the 2s, 2p, 3s, 3p, all the way to the end, and that's argon. And then from there on, you pick it up from 4 s's, 3 d's, and then when you get over here, you're back to 4 p's. If we were in this area, we'd be filling 4 p's. So that's the shorthand to introduce the noble gas, because the noble gases have complete orbitals, all of them. At that stage, everything above it has been filled to that point. Okay. And these are really the only ones you're interested in anyway, in a chemical reaction. You don't care about those. This is known as the core. These are core electrons. They don't participate in chemical reactions. These are the ones that do the reacting. Okay. Let's see. So you should be able to write the configurations for these other elements. Just follow along like I did before. Just remember, either use the diagonal or recognize that when you get to the transition metals, you have to back up 1 principal quantum number before you start filling Ds. So on the 4s, you back up to 3, and on the 5s, you back up to 4 Ds here. And on the 6s, you back up to 5 Ds here. When you get down here, which orbitals are we filling down there? Fs. And for the Fs, you got to back up 2. So if you're in this section right here, you got to jump down here and you fill up the Fs. This is 6, so it'd be 4F is here. And this would be 5Fs. I don't think I've given you any of those. We're gonna stay up here because that's where most of the action in living systems happens anyway. If you were taking general chemistry, the 2-semester version, I'd punish you with those. No, it's not that hard. You just need more time. We've only got 1 semester to cover everything, right? So we sort of have to skate across the tops of some of these topics. Oh, it's 11 o'clock. Is there anything that we need to talk about that we have? Okay.